So hi everyone, and welcome to this presentation. My name is Sébastien Dubois. I'm a lead programmer at Amplitude Studio. And today I'll talk about Dungeon of the Endless, and more specifically about rendering and procedural content generation. For starters, how many of you already heard about the game before this conference? Okay, and how many of you did play the game? Okay. So I'll start with a quick video showing you the game so we can all be on the same page. Let's go. Thank you. So this talk will be divided in 4 parts. In the first one, I'll introduce Amplitude Studios and the games we are working on. Then I'll talk about rendering and how we mixed different techniques with Unity to get the specific visuals we have in our games. And then I'll talk about the procedural content generator we have in the game and how it could be maybe reused for different contexts. And finally, I'll summarize the talk. And maybe if we have some time, we'll have some Q&A. So first, Amplitude Studio. It's a French game development studio that was created in 2011. It's based in Paris, France. And we have a very specific link with our player community. We created the Games Together, a community platform where we have a lot of exchanges with our players. And so we gave them updates on the progress on our different projects, and they can participate to the creation of the games from alpha to release. The first game we released was Endless Space. It was released in 2012. And it's basically a 4X strategy game, 4X standing for explore, expand, exploit, and exterminate. And it's basically like Civilization in space. In this game, you have to conquer the universe either by strategy, trade, science, or war. And you can fight your opponents in epic cinematic battleship fights. And we were very proud last year to go back home from Unite with two prizes, the Golden Cube and the Community Choice Award. So after that, we started 2 new projects. The first one is Endless Legend, and it's once again a 4X game, 4X strategy game, but this time taking place on a 3D terrain on the planet. So think of it as a civilization with dragons, basically. And in this game, you have to find a way to make your people and the planet it's living on to survive the extinction. It's currently on Steam Early Access, and we are planning to release it pretty soon. And the other game, obviously, is Dungeon of the Endless. And it's kind of the missing link between those 2 games. Indeed, you start in a battleship coming from Endless Space, and it's crashing on the Auriga planet, which is the Endless Legend planet. And so in this game, you have to lead a team of survivors, and You have to make them crawl monster-infested dungeons and find the exit of those dungeons, and make your way to the surface of the planet, where you will start a new civilization, and that will occur in Endless Legend. We are also currently in early access on Steam, and we are also planning to release pretty soon. This game is a mix of a lot of different concepts on the technical side, as we will see, and also on the game design side. It is what we call a roguelite dungeon defense game. So it makes basically two main concepts, which are the roguelike, where you have to crawl randomly generated dungeons. You have hardcore difficulty, like permadeath of your heroes and stuff like that. And you have also the tower defense components, where you can forge the path of your enemies and place defensive turrets on it to damage them before they can get to you. We also have a strong RPG side on the game. You have heroes with specific attributes, specific skills, and so specific gameplay you will have to adapt to play the game. And we also have incoming persistent storytelling in the game. And finally, we mix two usually opposite kind of games, which are the turn-based and real-time strategy. And if you play the game, you saw that you have some planning phase, and you have the door opening that triggers new turns, and you have to resolve those turns in a more action-like game. Okay, so that was for the introduction. Let's talk about rendering, and more specifically, how we mixed different rendering techniques in Unity to get the particular visuals we have in the game. So from start, we wanted to have pixel art in our game, but not just pixel art. We wanted something more, something that would give more life to the sprites in the game and make them detach more easily from the background. So here is one of the first mock-ups of the game. So you can see that we started the design of the different units. And here is a screenshot of the first prototype. And pretty early on, we introduced dynamic lighting and shadows to the game, so we could have specific visuals. Then we had a lot of iterations on the atmosphere of the rooms, on the colors, on the sprites. And finally, we have this kind of visuals in the games. And we are pretty happy with it. So we'll discuss about how we achieve these visuals and what kind of difficulties we had to face. So the objectives of the game was to get pixel art, obviously, dynamic lighting and shadows. I'm not sure it's pretty easy to see here, but anyway. And we also have more modern stuff like particle systems. One thing to know is that at the time we started the project, we didn't have any 2D pipeline or asset store plugin that would match our needs at the beginning of the project. So we had to develop our own sprite and sprite animation system. So when you want pixel art in your game, you want to have what we call pixel perfect rendering. But what is it exactly? So it's pretty simple. What you want in your game is to have exactly what the artist designed showing on screen. So let me show you a quick example. Here's the demo scene. On the left side, you have what represents the scene of the game, and here is the screen of the game. So we want exactly what we have in our scene shown on screen. We don't want anything like stretching, for instance, of the sprites, because stretching will actually get some weird line duplication on screen. It occurs in both axes, so we don't want that. We also don't want any kind of blurring effect, like this kind of thing that could alter the visual of the game. And yeah, that's pretty much it. So here's what we don't want. We don't want any kind of stretching on the sprites. We don't want any missing or duplicating lines of pixels. And we don't want any kind of blurry textures. So let me set it back to the original configuration. So the old school rule of thumb is to have basically one texture pixel rendered by one and only one pixel on screen. But this was the case in like 10 or 20 years ago. But now that we have much higher resolutions, we can afford to get some zooming effects on our sprites to reinforce the pixelization of the game. So basically, you will have, if you apply like a two-factor zoom on your game, you will have 1 pixel of texture rendered by 2 by 2, so 4 pixels on screen, and so on and so forth. For instance, in our game, we have what we call a gameplay resolution, which is of 640 by 360, and it's kind of the field of view we want to give the player. It's the amount of pixel basically we want him to see. So in higher resolutions, we apply a zoom, a 2 or 3 zoom factor, and for resolutions in between, we give the players a choice to either have black borders around the screen or to stretch it, but in this case, it will not be pixel perfect anymore. So how do we achieve pixel perfect in Unity? Well, we have 2 things to configure correctly. The first one is the camera. So if I go back to my scene, you can see here my camera, and it's configured in a specific way. So we don't want any kind of perspective in our game because it would, once again, have some weird effects on the sprites. So we want isometric view, so we use the orthographic camera. And once you use this orthographic camera, you will see that a new field appears, and it's named size. And this size should be equal to the half of the screen height. So in our case, the screen is rendering a 64 texture. So the camera should be set to have a size of 32. The other thing that is really important to configure is the camera position. As you can see here, I have a small marker on my sprite that indicates the position of the camera. So you can see that if I move freely my camera around my sprite, I get these weird effects with line duplication. So the principle is to snap the position of the camera to the pixel grid of the scene. So here, if I hold the control key and snap the position to the actual grid of pixel, you will see that we don't have this alteration anymore. So that's what we need to have on the camera. Orthographic projection, size set to the half of the height of screen, and snap the position of the camera to the pixel grid. The other thing to configure in Unity is the texture import settings. So here is the texture I'm using for the sprite. First of all, it's an advice, you always want to use the advanced mode of this tab in Unity, because you don't want Unity to hide from you any kind of configuration it would make. By default, it's set on texture, but you can see that if I go back to advanced, it has triggered some configuration like generation of mipmaps, and that's, for instance, a kind of thing that we don't want in our game, so we disable it. Sorry. Second thing is you want to use the point filter mode. You don't want any kind of linearization of the sprites. So if I use it, you will see that I have some weird borders appearing around my sprite, and we don't want it. You also want to set correctly the size, the maximum size of the texture for your build. So for instance, if I set it wrong and I set the 32 size, I will get really ugly results. So I set it to the correct size. And you also don't want any kind of compression. If I use this compression, for instance, you will see that it's not easy to see, but you will lose some colors in the sprite. If I set it back to the good compression rate, you will see that I go back to the original colors. So you want to use the RGBA 32 bytes compression. So to summarize it, no mipmaps, point filter mode, adjust the maximum size of the texture, and don't use any kind of compression. Okay, so now we have perfect pixels in our game, so that's cool. Let's go ahead with the next technique. What we want to use is dynamic lighting and shadows, and more specifically shadows. That's what we will talk about. So it's not obvious when you see the game, but actually the dynamic shadows needed to have 3D geometry in the game. So if I show you a snapshot of the game, it's a typical scene you can see in the game. Whoa. So on the right, you can see what the players will see on screen. So it looks pretty much 2D, but actually, when you look at the scene of the game, you will see that everything is rendered in a 3D setting. So I have my sprites here, if I focus on this one. And you can see that it's a flat quad that is rendering the sprites, and it's the case for all the different elements of the game. And we use the Unity lighting system to have our shadow system. So if I move this point light, for instance, you will see that it updates dynamically the shadows of the different elements. You can see that they are casting shadows on the ground, but also on each other, on the different elements of the game. So that's how it looks in the scene view. When you look more closely, you can see that our sprites are stretched in a weird way. If I move it close to the original size of the sprite, you can see that it's been stretched and it's taller than it should be. And let's see why. Let me show you another scene. So here I have set up a very simplified view of the game, version of the game. So we have basically here in the scene the ground, the wall, and the sprite in the middle of my room. You have this point light that is used to get the nice shadow we see here. And we have the camera, which is right here. And in this configuration, you see that we have the camera that is facing the sprites. So we are missing some part of the scene. We are not seeing the ground, for instance. So to have a view on all the elements of the game, obviously we have to rotate the camera around it. But once we do it, you see that everything gets stretched on screen. So to fix that, we have to scale our scenery to get back to the original sizing of the different sprites. So that's why we have some weird scaling in the game. Here is the math that gives you the scaling of the Y and Z axis depending on the camera angle. And we choose to have 60 degrees camera angle, so we could have an integer number as a scaling for the Y axis, because we wanted to minimize the floating point numbers approximation on this axis particularly. Okay, so now we have 3D scenery with shadows, we have pixel perfect. What could go wrong? Well, as we are using orthographic camera, we discovered that it only supports forward rendering. It doesn't allow any kind of deferred rendering. We discovered it on the forums. And even if you can set it in the camera, here, you could set it to use deferred rendering, but so the option is not blocked, but it will have no effect. It will be like you would have chosen the forward rendering. So forward rendering has some limitations, like the fact that you can only use one directional light for casting shadows, and it was very far from enough for what we wanted to do. So we had a problem, but the solution was pretty easy actually, and we had to use the shader magic. We discovered in the surface shader documentation that we have this nice little pragma that is called full forward shadows that will force, in fact, the rendering engine to cast shadows even in forward rendering. So we just have to, you see on the line here, we just have to add this option, this pragma, to the surface shader configuration. And that's it. It works. Yeah. So we have pixel perfect, we have cool shadows in the game. What could we have next? Well, we wanted to have more bumpy sprites. We found an article on the dev blog of another game, which is Legend of Dungeon, And we saw that they used a very simple technique, but that has pretty good results, which was to not only have the diffuse part of the sprite, but also use very simple normal maps based on grayscale textures to have a more realistic kind of lighting in the scene. So let's see it in the editor. So here you can see we have two versions of the same sprite. The first one, which is called flat, is actually just using a simple transparent diffuse shader. And the other one is using the transparent bump diffuse shader. And you can see that for the normal map, we are using a very simple texture, which is like this. And basically it tells the engine to render the sprite as if it was like a cylinder, in fact. So you will see that when I move my point light here, the two sprites will react differently to the light. So you can see that when I move the point light closer, both of the sprites will get lit completely. But when I move it sideways, you will see that the first one will get unlit on every pixel the same way, but the other one will get unlit only on a part of the sprite, only on the left or only on the right. So it's like we have some 3D running in the sprite, and that's a cool effect we wanted in the game. It's pretty simple to achieve, and the result is pretty good. We are also using this technique for the textures of the scenery, like the ground or the walls. You can see here that we have this texture that is used for a ground in one of our rooms. And we also use the bump diffuse shader with this time simply the same texture as the diffuse, but in grayscale. So if I open the texture used for the diffuse, you can see that we are using this part for the quad. And if I move to the next image, you can see it's just a grayscale version of the texture, and we are using it as normal map. And it gives a pretty decent 3D effect on the lighting. You can see that the small shadows are appearing on the borders on the different parts. Okay, so that concludes the rendering part. So yeah, we have now sexy bumps on our sprites. And we are pretty complete. Then several months ago, we decided that the Unity 2D pipeline was robust enough for us to use it, so we migrated to it. We wanted to benefit from the sprite packing system. If you don't know what it's about, it allows us to have this kind of sprite sheet, which is 1K by 1K, reduced and compressed to have something very much more optimized in kind of space repartition. So here you can see that we end up with a 500 by 500 pixels. And so we reduce the memory footprints on GPU and also the size of our builds. We also wanted to have access to the animation editor of Unity, which is pretty useful. It allowed us more complex animations than the one we developed ourselves. And we also wanted to have access to Mechanim, which gives much better animation transition scenarios in the game. But we faced some difficulties. The first one was about the data migration. We had a lot of hard time to find how to do it. There was some part of the documentation that was missing for the sprite structures, for instance. So we had to do a lot of hacking of Unity, like modifying the meta files of the different textures. So it was a lot of work. We couldn't do it by hand because we had 3K sprites and a little bit more than 1K animations. So we had to automate it. We also had a lot of work on the code side because we had something that was closer to the legacy animation of Unity, and we wanted to transit to something that was Mechanim, which is more complex. And we also had to change our 2D pipeline and especially the shaders. And we had to encode the Bumpy sprites that we saw earlier in the alpha channel of the sprites. Okay, so that was about rendering. Now let's talk about the procedural content generation and more specifically the dungeon generation we use in the game. And you will see that it's pretty simple system that could be reused for other contexts. What we are generating in the game is something like this. So this is the typical dungeon. We have rooms that are linked together by doors. That's basically what we want to get in the scene. Even the ship that you see in the beginning of the game is basically a room. So that's what we want to have. We had two major iterations on the generation system. The first one was completely code-driven. So we had no kind of editing tools or any kind of level design system. So we had everything configured in XML files, basically. Here is the high-level algorithm we used for it. So basically, it was pretty simple. We placed the starting room of the game. This room had one door, so we select this door, and we place a randomly generated room behind it. And then we had some randomly generated doors, and we go on and on until we have no more doors in the system or we have reached the dungeon size we wanted. So here is what it looks like. So we place the first room with one door. We pick this door. We place a randomly generated room behind it. And then we place randomly generated doors. And we go on again. We pick one of the three. We place a room, add some doors, and so on, and so on, and so on, until we get the maximum size of the dungeon. So here is the kind of generation we had. So you can see that we have different kind of rooms, different shapes, different sizes. The doors are placed nicely on every kind of wall. And here you can see another iteration where we added modules for the players. So we had randomly placed modules. And then we had this last iteration where we tried to add some randomly placed props and lights. But as you can see, it's not really satisfying because the props are overlapping with the modules. And some rooms get weirdly lit. So you have some parts of the room that are completely unlit. So it was not really satisfying. Well, we had some pros in this version. We had pure randomness, so we could not find any kind of recognizable pattern in the dungeons. And it was really simple to change the kind of generation we had. We could have a lot of variations with simple parameters like maximum size of the rooms, the number of doors by rooms, the kind of space we leave between the rooms, and so on. But we heard some feedbacks that was not really satisfying. So yes, the game designer was finding it too random. The artist was not really happy with the final result. And the players could find it unfair because the gameplay, the difficulty is really closely linked to the way we have the layout in the rooms. So the major flaw of this system was that we were missing a lot of control for the game design and the artistic parts. And every time we wanted to add a new constraint to, for instance, to place in a certain way the props in the rooms or to have a certain layout in the dungeons, we introduced a lot of complexity in the code. So it became very quickly something really hard to maintain, and it would not support the kind of iterative development that we have in our game. So we switched to another kind of generation, which we call semi-procedural. What does it mean exactly? This time we learned from the previous version, and we wanted to have the end on the level design. So we wanted to have some tools to allow the game designer to place different kind of rooms in different layouts. We wanted to have artistic composition, so we wanted to be able to get something beautiful. And we obviously wanted to have something maintainable that will support the iterative system. So here is how the design process works. First, we design the contents. So if it's level design, we design a dungeon layout, for instance. Or if it's more artistic, we design a room composition. Then we abstract this design. It means that we try to extract from it the important aspects of it. If it's a dungeon, for instance, it will be the shape of it, the length of it. If it's a room, it will be more like the placement of the different props, the atmosphere we want to give. And then we feed it to the system, and it will generate new designs from it. So we say that we design by abstraction, and we generate by specialization. Let's see how it works in practice. So let's open this scene, if I manage to do it. And you will see in this scene that we have a room composition, which is here. So the artist basically designed this room, and let's say he's pretty happy with it. So this is the design, and we want to abstract from it. So we basically look at it and we say, okay, what do we have here? We have two big props on each side of the room. We have two tall ones in the back, and we have some medium-sized stuff going on the wall. So we create what we call a template. A template is basically a model, a version of a room, for instance. And inside this template, we use slots. It's the blue cubes you see here that will represent the kind of content we want to put in this template. So you can see that we have those big blue boxes that will match the big props we have here. We have the two tall ones that will match these props, and we have three small props here. So we have this part in the system, but we also have a database of other templates for different kind of content. So we can see the dragons that appear here. You can see the different boxes and stuff like that. And so when we feed it to the system and we generate a room, you will see that we keep the same layout in the room, but we use different props to populate it. And you can see that we have something that is pretty similar to what we had at first, but with a lot more variations. And we use the same system on the dungeon level. And I'll show you this with this other scene. So here you can see a level design of dungeon that we are pretty happy with. And as for the room, we will not just take this design, but we will abstract it and create a new template, which is this gray box. And we will place slots instead of the actual rooms of the dungeon. And we also have a database of different rooms for the different sizes and different shapes. And once we hit the generate button, we will get some new dungeons like those ones. And you will see that we keep the same layout, but we have different content in the rooms, different sets of props and stuff like that. So yeah, that's how it works. The high-level algorithm is once again pretty simple. We place the initial slot, which is most of the time a dungeon slot. And until we have some slot in the scene, we select a random one, and we replace it with a template that is matching the type of content. For instance, a room with a certain shape and certain size. And we do it recursively until we don't have any slots anymore. So in the example I've showed you, we have three major types of content, which is the dungeons, the rooms, and the props. The dungeons are containing rooms, and the rooms are containing props. But it was not enough because, as you can see, we have pretty much the same dungeon, except for the content. So the players will pretty easily recognize the patterns. So we introduced a new level of abstraction, and we called it the room packs and the props packs. So it allows us to have more levels of abstraction. And as you can see, instead of placing the actual room slots, we are using room packs slots that are pretty big and that will represent basically groups of rooms. And we also have, obviously, templates of different kind of room packs. And once we give it to the system, it will generate, once again, new dungeons. But this time you will see that we have much more variations on the layout. So we keep the general aspect of the dungeon, which is pretty much across, and we have a lot more versions of it from the same design. So that's actually how it works. And I could show you how the generator is acting, actually. Here, so I will hide these ones, clear this one. And we will launch the generator in the step-by-step mode. And you will see that we place the initial slots, and one by one we replace it by the content of the template. So you can see that we have replaced the room packs. Now we are replacing the rooms. And in those rooms, you can see that we have props slots. And that will get replaced one by one. So it's the same system for each level of abstraction. Thank you. On top of that, we have several features that are pretty useful. The first one is the tag system. We can place some tags on the templates, and it will correspond to attributes or properties of the templates. And on the slots, we can add what we call constraints, tag constraints, that will control the template picking we have during the generation. And those constraints can be either mandatory or forbidden, and can be applied locally on the slot, or recursively in all the slots that will be generated after that. So if I go back to my room example, we'll try to use the tag system. So here you can see, if I select my templates here, we will focus on the big props. So here we have 3 versions of the dragon, basically. And you can see that we have here the tag that says it's a brown version of the dragon. Here also you have the brown tag. And on this one, we have the black tag. So we could constrain the generation of this room by saying, for instance, I want this particular slot to only use the brown versions of the dragon. So I use a mandatory tag, and I set it to be brown. And if I generate another room, you will see that we only use the brown one on the left side. But on the right side, you can have the black one. We can also have the opposite system. We could say that we don't want any kind of brown asset on this slot, the right one. So we use a forbidden rule. And once again, we type the brown tag. And if you hit generate again, you will see that we only use the black one, actually. So this is how it works. We are also using the same kind of system for the dungeons. For instance, we have several environments in the game that have different kind of atmosphere. And so we want to constrain the generation for each level to a certain environment. For instance, in this one, you can see that we use the laboratory environment, but I could also use, you can see the recursive mandatory tag here, which says I want the tie set to be laboratory. I could use the sewer and generate again. You will see that we have a completely different atmosphere in the colors and in the lighting. Here, you can see it's a completely different environment. And I could also have no rule at all on this generation, but in this case, you will see that we have pretty inconsistent kind of results. You will see that we mix all kind of different assets, all kind of different rooms. So it looks pretty ugly, but it's just for demo. Okay, so that was about the tags. We also have a really simple system that gives us a lot of variations in our generation, which is called the slot probability. By default, every slot should be used in the generation, but we can say the system that certain slots should be only used sometimes, but not always. So I'll go back to my room, and I will say that this one is cool, but I don't want it every time. So let's set 0.5 probability. So you will see that we only use it one time over 2. So it gives us new variations, and we can apply the same rule for this one, and you will see that we get totally different generation just by using this simple slot probability stuff. Okay, and so that's the kind of generation we get in the game. So you can see that it's pretty complex, pretty diverse. We can have control on the level design, so on the difficulty of the game. We can make it fun, we have the control of it, and we also have pretty beautiful results, and we are pretty satisfied with. Okay, so let's go for the pros and cons of the system. So the pros are obviously the objectives we wanted at first. So we have a hand on the level design. We can do some artistic composition. And the code is very simple and evolutive because we can easily add some new rules to it without breaking the system. And we have very scalable content. Every time we introduce a new template type or a new template or new kind of slots or etc. or a new kind of level of abstraction, we are multiplying the number of possibilities by a great number. And finally, we have one editor for every people in the team. For me, the programmer, for the level designer, or for the artist, we are all using the same tool, so it's easier to maintain. But we have some flaws that we are dealing with in this system. Obviously, we have less code work, so we have more integration work. But for me, it's not really a system. It's not really a problem. We have the door system, which is a pretty strong constraint. I could show you this in this example. We are actually using the tag system for the doors. For instance, you can see on if I take this template of room, you can see that we have 4 tags corresponding to each of the doors that we can have in this room. So we have the north, it means door north, south, east, and west. So we flag the room saying we can have all those 4 doors. And on this one, for instance, which is just an horizontal corridor, we only can have the west and the east side doors. And we apply the same system on the slots. Here you can see that, for instance, these rooms should be linked to 4 other rooms. So we have a mandatory rules that says we want to have all the 4 tags. So we can see here. And for this one, for instance, you can see that we only have 2 constraints that says we want the west one and the east one. But as you can see, we are using only 4 directions for the link between the rooms. So sometimes it can lead to some recognizable patterns in the dungeons. But it's pretty easy to fix because we just have to add new version of the rooms or trick the system by hiding some parts of the room, and it will look like it's not really symmetric. Okay, so let's summarize it. First, we saw that we used a lot of different techniques for rendering and to get the actual design we have in the game. So we used pixel art, we used dynamic lighting and shadows, and we also used normal maps for the bumpiness of the sprite. And in the second part, we saw how we control the randomness of the dungeons by injecting handcrafted contents. So, and as I said, we design by abstraction, and we generate dungeons by specialization. And that's it for the talk. Thank you. So we have some time left, so if you have any question, I think it's better if you use the mics that are on both sides of the scene. So let's go. Or you don't have any question. Here you will see my contact, so you can reach me if you have some questions. I have one question there. And you have also the links to the game and to the slides I've just shown you. Yeah?
So you show the camera snapping to a pixel grid,
yeah.
And it seems like you're probably using that target as an essential component of that, but I have no idea how I would implement that to make even the target snap to a pixel grid as it moves across the sprite.
Yeah.
So how do you do that?
So you're just talking about the demo scene or inside the game?
So when you were moving the camera just across the surface of the sprite for one of the characters?
Yeah.
And I'm not sure how to make that camera target snap that way.
Well, basically you have, in our camera management system, we say that if we move the camera, we have a virtual position of the camera, which is a floating point coordinates. But we snap it, every frame we snap it to the closest point on the grid, basically.
All right, so yeah, it seemed like that was some sort of prefab camera thing. I'm like, I don't think that's possible with the cameras it's written, but you're just scripting to grab,
by
okay,
scripting,
this is the right point. Okay.
And we are doing the same for the different entities in the game. So our heroes have also a virtual position, which is a floating point coordinates, and we snap it to the ground,
right, so they line up pixel perfect with their backgrounds. I see. Okay, thank you.
Hi. Do you generate your levels at build time or run time or?
It's at runtime.
Runtime? Okay. So anytime you go to a level, you just generate it? How long does it take to generate one?
It takes, the first level takes between 2 and 3 seconds.
Okay.
But we had a lot of other things going on additionally to the generation, to the pure generation. So we are instantiating the heroes, the different kind of things. So let's say it's 2 seconds, and for the biggest dungeons, it should be 3 or 4 seconds, nothing more.
Thank you.
Can you talk a little bit about how you did path finding after generating your dungeons?
Yeah, but that's the kind of thing we do after generation. We use the A-star pathfinding project plugin, and we just run the scan after we completed the generation, and then we have the grid for the pathfinding. And
So
every time we open a new door, we recalculate the pathfinding, especially on the part of the door that is opening, so we can link the rooms with each other to have the complete path of the dungeon.
Thank you.
Could you talk a little bit about how you set up your artists actually designing the templates and what tools you built to do that? Because I noticed a lot of like snapping and stuff required in there to make it look clean. I'm wondering what you did there.
All the tool set is made to be simple to use, especially for the level designers and the artists. And for instance, I showed you the doors tags. You don't have to set it manually because it's a pain to do it. So the system will basically, you just have to hit a button, it will scan the template, and it will place automatically the different door tags that you will need in the generation. So we had, we have a lot of optimization. Every time for instance, you get this slot, you can change the type of it. Let's say we want a medium corridor, which is horizontal. It will automatically change the shape of it. So you can easily see where you should place it. You just have to place it manually without caring really about the snapping. And we also have a feature that will snap automatically all the slots so that the doors will match. And
And the same is true for the level templates themselves?
Yeah, on every level it's the same system. So yeah, it can be applied on every level.
Thank you.
How did you address Z-depth fighting amongst players and enemies, and you know, when they're
For the rendering?
Yeah, for the rendering.
It appears I have a demo scene for that. That's something I wanted to show at first, but I didn't think I had enough time. So here you can see an example where we use transparent diffuse shaders. And even if my blue circle is in front of the red one, you can, I'm not sure it's what you were talking about, but you can see that we have some weird stuff going on when we move the camera. And so the way to fix it was to use cutout transparent shaders. And we are using the same textures on both sides, but on this one you can see that we use the cutout diffuse shaders. And we don't have this kind of weird bug of the Z fighting. Yeah, and that's how we solved it. At first we used the rendering queue index in the materials, but it was not really efficient because it was pretty hard to maintain, and we add a lot more draw calls because it will duplicate the shaders, the materials for the different sprites.
I have a couple questions about the scaling of the sprite geometry to compensate for the camera angle. It looked like as you were playing with the other pieces of the dungeon, they were not scaled.
Yes, they were.
So, they were? All right. So was that step something that was manual, or was that something that you just had a script that ran through the dungeon and scaled all the...
Oh, we do it at runtime. We have, all the tools are using the 1:1 scale.
All right.
So we have the good view of what we are using. And then after we have generated the dungeon, we scale it so we can have the good rendering.
And in choosing that solution, did you ever explore trying to come up with custom camera attributes to tweak the camera to solve that problem before you landed on this?
Yeah, we did some pretty tricky things, like as the problem was to use an orthographic camera, we tried to go back to something using perspective. And but we didn't want perspective, so we cheated and we set the field of view to the minimum value, which is 1. But as you can see, you have only a view on a very small part of the game, so we had to move the camera very, very far away and set the clipping planes, obviously, so we could have a better view on the game. It's pretty hard to do. Wow. I'm too far. It's hard to do because you are dealing with really great distances. So we have this kind of stuff going on. But as you can see, I'll switch to show you the game view. As you can see, you have weird stuff going on the rendering parts. As I move the camera to get approximately the same amount of pixel, you see those weird stuff going on, because when you deal with such great distances in Unity, I think there's some kind of floating point errors that are impacting the render.
Change the near value as well.
We also changed the near value. It was pretty much the same.
A lot bigger.
Yeah, that's what we did. Oh. Like something. Well, anyway. Well, we tried to reduce it to only the part of the dungeon we wanted to render, but we had the same effect. And we don't have exactly an isometric view, so sometimes we could see some weird white lines appearing on the borders of the walls, so it was not satisfying at all. We didn't find any setting that will allow us to use this kind of configuration. But that's what we tried first. Yeah.
Hi, I have a couple questions. The limitation on the lighting for the forward renderer is primarily for performance reasons.
Yeah.
Just disabling it, didn't that give you performance problems with having so many lights?
We have a lot of draw calls actually in the game. We are working on the optimization of it. But yeah, we have, by room we have, if I zoom in, the dungeons, you can see that we have approximately 4 lights by room. So it means a lot of rendering. So we have here this one. But most of the time we are using this kind of light just to have the atmosphere of the room. And we have only one light that is casting shadows. So we don't have a lot of shadows that would make it pretty hard to read. And so yeah, we are trying to limit the range of the lights. We have also a light blocking system that is not appearing here. Oh yes, you have this kind of blocks that are used just to hide the lights between the rooms, so we don't have, this room will not impact the other rooms. These lights, sorry, will not impact the other rooms.
Okay. And then my second question was compressing your normals into the alpha. So
Yeah.
are you just using 1 bit for transparency and then
Yeah.
7 for the normal?
No. We use the full alpha channel for the transparency, and it gives us the angle of the normal map that we should use.
Good. Thanks.
Okay. I think we don't have any more questions. I'll give you back the links. Thank you.